Brent next. It's an honor to have Brent, and I still remember the amount of energy he brings to a talk. So I look forward to him sharing the same energy with the rest of you. I have a very brief intro for Brent. So he's currently a senior VP and chief scientist at 3D Systems. Many of you may recall him being the co-founder and CEO of 3D Sim back in the day. Fun fact, Brent has been a testifying expert in high-profile patent litigation cases within AM industry since 2002. So hopefully your paths haven't crossed in that sphere with him. And more importantly, Brent recently became a grandfather, and he enjoys traveling with his growing family. Over to you, Brent.
Yeah, thank you. Today, I'd like to talk about something a little different than what I normally talk about. Hopefully, you can hear and see me fine. If not, let me know. But I'm going to do this from a slightly higher level than everyone else's, and think about the role really of an entire software platform instead of the pieces. And so, first of all, let me just talk a little bit about 3D Systems now that I'm there. Some people wonder, why did I join 3D Systems? And one of the reasons is because really it's gone through this rebirth in the last couple of years. And for those of you who know the history of additive manufacturing, 3D Systems was the first company in 1986. And for the first 34 years, it did a lot of different things, but really about a year and a half ago, decided to really focus back onto the core of additive manufacturing, and is really sold off a bunch of non-core business units and is really growing its core business in additive manufacturing again. So I'm excited to come and be a part of this sort of rebirth of 3D Systems. And when we think about 3D Systems as a whole, we have a very large portfolio of additive manufacturing technologies, metals, plastics, and then supporting casting and all kinds of things. And in addition, we have literally more than 100 materials we sell on different platforms for different applications. And so when you think about the types of solutions we need from software and design for additive manufacturing, we like to think this in a much bigger realm than some of the work I've done in the past, as well as some of the work presented here today. And if we go beyond that and just think about, what are the types of things that 3D Systems has done traditionally, it's more along the lines of what would be like our 3D Expert or 3D Sprint products, which if you're familiar with those or not, I'm not sure. But they're more the traditional things of importing data and positioning and putting supports and setting up the build and then sending that build to the machine and running it. And so there might be some simulation tools built in. And in fact, in 3D Expert, we do have some simulation tools built in. But even though it's integrated, it's still quite manual in its operation. And so one of the things that you may have noticed if you follow, industry, the business acquisitions, whatnot going in software, is that 3D Systems just acquired Octan. And a number of people were like, why are we buying Octan? In fact, when I joined 3D Systems, this acquisition was well underway in its process. And I had questions about what's the goal here? Why are we looking at something that's not focused on a specific machine or material? In fact, isn't even just focused on additive manufacturing. Why are we looking at something much broader? So I'd like to give you a little bit of feel for that today by showing you a couple of videos that lay out, what the goal is here, what Octan can do, and then we'll dig into a little bit of the details first. So let me first start with this video. I think my audio indicated it's not going to play the audio properly, but we'll see here.
Industry 4.0 is just beyond the horizon, promising a new age where humans and machines work seamlessly together, and where digitalization and automation pave a new way of manufacturing. Take the example of welding. 100,000 welding robots are installed every year, and while they are fast, they are not smart. It can take weeks to program them, and when they're finally up and running, up to 30% is typically wasted due to process inefficiencies. This is exactly where Octan comes in, harnessing the power of artificial intelligence to teach robots how to learn from their mistakes, recognize patterns, apply past techniques, and even literally listen out for potential faults and take immediate action. Octan's scalable manufacturing operating system can not only connect 3D printing and CNC machining, but any manufacturing workflow across any type of hardware. It also tightly connects the production environment to existing business systems, enabling detailed traceability through a full digital thread for any size company. That's how Octan accelerates the pace of change, bringing smart automation closer than ever.
All right, so that was the first video, and I think you saw in there, this idea. Okay, there's a software platform opportunity, and we showed in this case something not additive manufacturing, welding related. How do we plan welding? How do we design a workflow? Now let's dig a little bit more into the additive. Then I'll little video here on the additive side. Pull up another video, and go from this here.
At Octan, our agnostic manufacturing operating platform automates the end-to-end workflow across and beyond the production floor. Octan combines order tracking, latticing, build preparation, slicing, CAM, and scheduling, and gives you full traceability and data insights. This is an all-in-one cloud-based platform that leverages artificial intelligence to automate every repetitive task, utilizes intelligent IoT capabilities to connect all the equipment on the factory floor, including plastic 3D printers, metal additive manufacturing machines, and even post-processing equipment. Octan empowers humans and machines to work seamlessly together. Our team of global manufacturing and AI experts can have you up and running within a day. Experience it for yourself.
All right, so let me get back to the presentation. And so I think what you saw there is this vision, right? And it's not just a vision, but it's actually a reality. Those applications that were shown there, we actually have things working. And so this Octan platform is really set up as a technology agnostic platform, but it's absolutely critical for additive manufacturing. And so one of the things unique about what 3D Systems is doing then in this space is saying, well, if we want a technology agnostic platform, then in reality, it can't just be focused on one company's machines. And so Octan is really designed to work on any number of machines. And in fact, we already have a whole bunch of agreements with different additive manufacturing technology companies, as well as companies in other manufacturing realms. And so then if we think about, well, what's unique about this? Because you've probably seen things like manufacturing operating systems or manufacturing execution systems, or there's PLM systems, ERP systems, all these different things that try to tie information together. And one of the unique things about what we're doing with Octan is we're tying this entire digital thread together, everywhere from design all the way through quality assurance, and using artificial intelligence at each step. And so what I want to go through in the last little bit of my talk here is, okay, if we're going to build this big platform, how do we begin to automate all of these things which today are very manual? And so let's take, for instance, just setting up the build. There's all kinds of things we do in this that, as we set up a build, that we could have artificial intelligence learn either from people or from simulation. And so here's an example of what we're doing in the dental space. Now, some of you may not recognize that 3D Systems actually has a very large dental and biomedical fabrication facility. We have those both in America and in Europe. And so we have a very large number of pieces of software before we acquired Octan that we use, things for bringing in software and importing it and healing the geometry and choosing the orientation and maybe hollowing a geometry, labeling it, generating supports. Then how do you lay these out in a machine and how do you send them to a machine? And from there, even how do you then monitor the post-processing, and so that you can have quality assurance in this for these biomedical or dental type applications. And so all of these steps are being added into the Octan platform as individual components that you can either manually do, or you can have artificial intelligence learn from you and then just do it automatically in the future. And so one of the things that is similar to what we've talked about, the other speakers have talked about today, is we have a tool in 3D Systems. We recently acquired Additive Works out of Germany, and they have Amphion. And Amphion is both simulation and also algorithm-based methods for doing things like the inherent strain simulation that Albert talked about before, for looking at thermal buildup in processes. When do you have overheating in parts? Predicting that. Where do we put supports? How do we do distortion compensation and those sort of things? And so what we can do is, for instance, with this Amphion product, which then can be called as a component within the Octan platform, we can automate the whole idea of orientation selection. And for different types of products, you may have a different criteria based upon, say, build volume or support, build time or support volume, or amount of post-processing or support removal or deformation. And it really is, those are sort of application dependent. So normally we set up Octan as for a specific company with specific applications in mind. You can start to trade it. What are the trade-offs for biomedical that are more important than maybe aerospace or automotive? And you can start to train this for things like selecting orientation, for how to place supports. Again, we have simulation that can design an optimum support, very similar to the type of simulation that Albert was talking about earlier in this meeting. And again, as a component, you can either run those simulations, or one of the things that I found from my research in the past is you can actually train artificial intelligence to predict the outcome of a simulation. And back in some of my prior work with other companies, we found that we could reduce the time by 2 orders of magnitude with almost no loss of fidelity of the prediction. So if you have good training data through simulation or from experiments, artificial intelligence can, about 2 orders of magnitude faster, predict the outcome of what you'll see, and use that to then make decisions early on. This is also true of areas like distortion prediction. And again, as Albert mentioned and others have mentioned, if you can predict the shape change, then you can modify those shape changes and do distortion compensation, as well as do things like predict where recoder interference might occur and where you might need to redesign. So in this case, design 1, as I'm showing here, has these little holes in it and some sharp edges. And those holes, as they connect back to each other, often give unique stress and distortion profiles that can cause blade crashes, where if you change that design, you can minimize the effects or chances of blade crashes in metal parts. I already mentioned distortion compensation. Gonna move on from there for just a minute. And so some of the other things you can do with our platform in general, again, this is simulation tool. You may have, for those of you who've worked in metals, you know that, say, different layers, when they have different amounts of cross-sectional area, will have a different amount of heat basically put in per layer. And so different regions of your part are going to get different amount of bulk heating and cooling, and can lead to maybe different microstructures as a result. So sometimes you want to even out that cooling time so that every layer has a similar maximum temperature it gets to after, say, 1 or 2 seconds after the processing. And so one of the things we often do is we can build in what we call ghost parts, or just have the machine, basically pausing in certain areas. And a lot of machines, you have to do something like add a minimum layer time. And for this geometry we're showing here, if you're adding just a minimum layer time, you're going to take a 22-hour build up to 225. But if you do some sort of intelligent machine learning and simulation driven, you can achieve the right microstructure throughout, but at 61 hours. Now, again, that's much more than 22 hours, but if the 22-hour one doesn't give you the right microstructure, then it's just trash anyways. So hopefully I've illustrated kind of where we're going with rethinking this whole platform idea of additive manufacturing, that we want to think about beginning and end and all the details in the middle, and how can we throw simulation where we need it, and how can we use machine learning. And I know I haven't gotten a lot of the details of how we're doing because it's only 20 minutes. But I wanted to sort of give you the vision of where we're going. I think this is my second to last slide, and just say, we can also apply the same thing to the monitoring and inspection. So this is also part of the platform. You can pull in the process monitoring, the inspection after the fact, and you can then apply machine learning to tie, for instance, what were my end result monitoring and inspection results back to what did my simulation predict for this step, and start to make the entire process smarter, or maybe apply a better inherent strain method than to get to and teach it over time to get smarter and smarter. So finally, really, we're trying to rethink this entire flow of things that we do in additive manufacturing, for metals, for polymers, for all applications, and say if we can design, prepare, simulate, schedule, monitor, analyze, trace, finish, inspect, certify all of these activities on a unified platform, we'll be collecting massive amounts of data. Part of that is simulation results, part of that is experimental results. And now we finally can apply these big data tools of of artificial intelligence that have been so powerful in other areas into additive manufacturing. So for me, this is really exciting, way to think about how to use software and how to put it together. And one of the last things I'll say is, this is an open platform. So all of you who've talked about different tools that you've produced today in your research, in your company, all of these things can be plugged in as a component into this type of an architecture. And so I encourage you as researchers to think about, hey, how could we, even early on in research, the nice thing about an open platform is you can plug this in today and start using it. It's not like you have to actually create a company. As long as you have a callable component, you can start to play in this kind of an ecosystem. And as a university, working with industry partners who maybe have this platform, or maybe you're a small company startup, it gives you ability to start to test what kind of a difference can what I'm doing today make in a larger operation. And so we're excited about building and putting out this open platform, because we think it's going to really take off and help industry get to the next level. So don't know if I have any time left, but anyways, thanks for the invitation. Happy to take any questions if I do have time.
Thanks, Brent. It does seem like the future seems quite promising for all integrated systems. I'm sure Andrew, who presented earlier about one of the challenges he had seen in terms of working between industry and academia, what your talk has kind of elucidated is there are entities trying to solve that exact problem. Perhaps we can see if there are one or two questions audience wanted to ask you. I think there's just a general comment from Richard Bibb saying, nice to see you.
Yeah.
Someone has raised. Yeah, Richard is here.
I do have a question for Brent. So Brent, thanks for the presentation. It's really good to get up to speed with what 3D is up to these days. Where do you see the balance of things going between metals and polymers? Because I see a lot of work going on in polymers, in metals, but not so much in polymers and certainly composite polymers. And I wonder what 3D's view is on polymers, and particularly composite and reinforced polymers.
Yeah, to be honest, we're putting a ton of work into that area, and I think you're going to see over the next year or two a revitalization of the whole polymer additive area as one that's starting to gain like the enthusiasm we currently have for metals. Metals, we've had this big sort of hype cycle. We're kind of now into the reality of that hype cycle. But if you look at things like continuous fiber composites or oriented fiber composites, if you look at the fact that we're starting to make photopolymers that have shelf lives and can run in environments like an under the hood engine environment for the entire life cycle of a car. We're starting to get materials that can last that long and are fire retardant and maybe aerospace grade out of all of these additive processes that have been around for more than 30 years. But until now, like stereolithography and other photopolymer based, were mostly for prototyping because you just couldn't get the life out of them. And so I'm really excited about some of these new types of formulations and new types of polymers. And I think that's really going to see a return of a new hype cycle on the polymer side, which again, for the people who are in academic and research, those hype cycles are really valuable because now you can get some money to play with some new ideas again, right? So yeah, I think you're going to see that coming again. So thanks for the question.
Thanks, Brent.
Thanks, Brent.